Hey, what's going on, folks? It's Mike here, and welcome to the next lesson in our modern C++ series. In today's lesson, we're going to continue our deep dive into the standard template library algorithms, looking at another numeric algorithm today, the inner product. So this is going to be familiar for those of you folks who have done some graphics programming or linear algebra, so a super important algorithm, but let's go ahead and take a look here. So let's go ahead into the numerics library here, and we'll go ahead and scroll down towards the bottom. And we're going to go ahead and see the numeric operations. Now, again, if you've been watching this list, you've probably seen iota. So we've done that previously, but today we're going to be talking about inner product. So computing the inner product of two ranges of elements. Again, my graphics programmers out there have probably done the scalar dot product. So let's go ahead and take a look at this here. So inner product, what exactly is this function? The basic idea is that we're computing the inner product or sum of products, which is, a common operation that, again, we use for dot product in computer graphics all the time. So let's go ahead and just, before I even get further into description, what that means is if I have something like, for instance, let's just take, some values 1, 2, 3, and I dot them, okay, with 1, 2, and 5. Basically what I'm doing is taking 1 times 1. So let's go ahead and label that, plus this next one, 2 times 2, 2 times 2, plus, and then the 3 times 5 here, okay? And I'll get a result of 1 plus 4 plus 15, which equals, if my math is correct, 20. Okay, so we made it through that. So that's the basic idea. But the important part about this, if we look at the description here, is it performs an ordered map reduce operation. So again, basically what I'm doing here is I'm taking pairs of elements here. So the first element here, then the second element, and the third element here. And those form the pairs, or we're sort of zipping them together, or in other languages, it's combining them together, depending on the terminology. We're mapping, so performing some function, which is multiply here, multiply, 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 and then adding, which is the reduce here, the result of all of our multiplications. So two sort of binary operations here. So I've got my multiply here and my plus operation here. So that is the sum of products. I'm summing up each of these products here. And that's the basic idea of map reduce. This idea that I get some data and maybe have more data here. And I'll just kind of draw a little, diagram here. Here's some more data. Here's some more data. And this is sort of pair 1, pair 2. And we can have as many, different pairs here, or tuples or collections, right, if these are more than 2 elements here. But then the idea is that I perform some sort of operation on this data. So in this case, that is my multiplication that we're doing on each of these pieces of data, right? I'm multiplying them. And then I ultimately reduce by adding all of these sums of the products together. So it's kind of interesting, if we think about these, again, thinking as a generic programmer, which is the goal of the standard template library, again, templates associated with generics, that idea of these different operations. So what if I could do something else other than multiply or add? Well, again, you can with the inner product here. So again, it makes it a relatively powerful but simple function. And this actually gets rid of a lot of our loops in our code. So anyways, let's just take a look at inner product here. We're going to look at the since C++ 20 versions, which give us const expr. That's the only difference that we're looking at, which is super great if we could do more stuff at compile time. And the basic version here is basically going to take in 2 ranges. So here's the first range specified by the beginning of that first iterator and the ending of that last iterator, and then the beginning of the first iterator. We don't need to supply the second one because we're going to assume it's going to, again, in lockstep, right? If I have 3 elements in my first to last range, I'm also going to have 3 in my other range. We could try to mess around with this later, or you could do an experiment, right? If you're missing one element or they're different sizes, I think it'll break, or it'll probably just generate you garbage. So you might want to do like a size check, or, these types of things. But I mean, those are the types of things you do. The building blocks aren't necessarily always going to provide that error handling stuff. That's up to you for how you want to handle that. So that's the basic operation for this. And you have an initial value. So again, if you're computing a sum, this is going to be like 0, or the sum of products, I should say. Now, in the second version here, we have two binary operations here. So that would be like our multiply and our plus here. Okay, and I'll make sure I get those in the right order. If those are in the map and reduce, I think they are for op1 and op2. The documentation should say or draw a picture or something. Let's see here in our parameters. Again, so here are our ranges that we set up in the initial value. Binary operation function that would be applied. This sum function takes a value returned by op2 and the current value of the accumulator and produces a new value to be stored in the accumulator. Okay, and then let's see this one here. Binary operation function that will be applied. This product function takes one value from each range and produces a new value. Okay, so this is the multiply, and then this is your final like reduce operation, I guess. Okay, so we'll just have to be careful with the ordering there. And again, we are just taking in input iterators, so you can watch my iterator videos to see that this is the, any of the standard template library collections, things like tuple and so on, will have input iterators built in for you. We might take a look at this in a little bit because I think it'll be interesting just to see how the loop-based version of how we would do this compares to, well, again, just having this nice function to perform the algorithm for us. Again, that way we can have no raw loops. Again, getting a more functional style, but it's a lot cleaner and we know what it's doing. And then we're also sort of thinking map reduce in this paradigm. Now, later on in this series, so again, make sure you're subscribed, but we'll talk about, how to parallelize some of these things, okay, and what that looks like, because there are other iterations or other things that we can do with other standard template library algorithms other than inner product. Okay. Let's see, which, spoiler alert, here it is, the parallelizable version, transform reduce. So, hold on to that. Let's go ahead and look at this example here. That's a good one for us to do here. Here, let's make our window fit here. And first and foremost, have to include the numeric library. I'm going to use array just to be a little bit different than vector, just so we can remember how array works. So let's go ahead and create an array, A and 0, 1, 2, 3, 4. That's reasonable enough here. And again, remember with C++ class template argument deduction, it'll figure out, these are integers or longs or whatever. And it'll even figure out the size here, which is kind of nice. If you have a fixed size array, which is, again, the purpose of array, otherwise use a vector. But again, if you forget to present the size here in the template, you don't have to worry about that. So I'll just show you two ways of doing that, just for the sake of remembering some of our C++ and how it's kind of neat that, C++, especially C++ 20 and beyond, is becoming more, readable, less of a pain to manage sometimes all the different arguments here. Okay, let's match this up here. And again, I'm going to be careful and make sure that I match the same amount of arguments here, but that's the point of being able to specify the iterators here. Okay, so for our inner product, let's go ahead and compute this, inner underscore product. I'm going to take the beginning of A, the end of A, and then the beginning of my B range, and 0 for the initial value here. Okay, so I'll match basically what they have here. So this is going to be the first sum of products that we are computing. Let's go ahead and call that sum of products. Okay. And we could, you could use auto here in case that's going to change, or you're going to accidentally, or intentionally pass in, floats or something here. But that's the basic idea here. So let's go ahead and print out that value. And we'll give this a run here. Sum of products. Let's print that out here. Sum of products. And an end line here, just so we see what's going on. Looks like it works. Sum of products is at 21. That matches the example they have. So again, 0 times 5 is 0. 1 times 4, that's 4, plus another 4, 2 times 2, plus another 9. That's 17, and then plus another 4 and 1. Okay, so that seems to be working. Phew, okay, perfect. So yeah, not too bad overall here for how this is set up. And again, we have some flexibility here because maybe your collections aren't always going to be the same size. In fact, let's try to break this. Let's see what happens. Let's compile and run this. It looks like it's got some built-in error detection. I guess it's just going to terminate. Okay, so that's better than I thought. so we don't have to worry. Or if I do something, I have the flexibility to, not all of my data is always going to be the same size here. So again, it looks like I have some flexibility. Now this one, it looks like it broke. I guess this collection can be smaller, or maybe I just got lucky and there was a 0. So actually I wouldn't count on that behavior. I didn't see it in the notes there, but you probably want to compute the sum of products of things that are the same size. At least when you're doing your linear algebra, your dimensions are the same if you're doing like a scalar product. So anyways, that's a nice example here. Let's look at the second example here. Or actually, let's recreate this, but first let's put in the binary operations to make sure that we get the same thing. So we have these things like multiplies, plus, and so on. So let's go ahead and try to do this again, just to understand exactly what's going on. I might get this wrong here, but let's give it a good old try. So this is going to be sum of products 2, just so we have something different here, and we'll make sure that we print that out. But I want to use the second version that takes in 2 operators here. Now we have these ones like standard, like multiplies and plus and so on. So these ones here, I think these are these in functional? Yes, we're gonna have to include this functional header. Let's see exactly what we have here, because I don't always remember. But these will implement these binary operations. Binary, again, I have 2 arguments, a plus b here, or x plus y, the operation plus here. Okay, so I have plus, minus, multiplies, divides, modulus, negate, a bunch of these here, equal to, and so on. So let's go ahead and try to do this, re-implement sum of products. And I'm going to need to include functional here. All right, so there it is. And so I'm going to, I can't remember, let's see, let's try to learn it from the documentation as we do on this channel here. Let's go to our operation 1. Okay, the binary operation function that will be applied. This sum function, okay, takes a value returned by op2 and the current value of the accumulator and produces a new value to be stored in the accumulator. Okay, so this is working with our accumulator, so I feel like this is part of the reduction part here. So I feel like that should be plus. Let's see if I'm right. And let's see if I write these out properly here. If I want to use plus, I think I can just pop it in there and it'll work here. And then that will make the other one multiplies. Oh yeah, I do need to put the empty template arguments and parentheses. Okay, so let's go ahead and do that here. And then standard multiplies. There we go. So it compiles and runs, and it gives us the result here. Okay, so again, that's why I find it's helpful just to understand or think about this as map reduce. Then you can read the documentation and kind of understand what's going on here. I mean, let's just for fun here, plus plus, okay? So now we're getting a sum of additions, not products, because we're just doing a plus here, okay? So again, if you, if you get these wrong here or aren't sure what the order is, or how to spell multiplies, you can just try and see if your compiler helps you out here. There you go. So if we do the multiplication of the things that we're adding, let's see, this thing's just going like totally bonkers. I mean, since we're multiplying everything in our accumulator and it's 0 to begin with, this just isn't going to work here. So maybe we need to do 1 and we'll get some multiple of the multiple of products is what this is. But, already giving us some interesting results here. Now, I'll tell you what the second result is here, but I want us to think about it just a little bit. Let's leave this. Let's rewind so we get it in a correct state. There we go. Just so we have our good code. But something you could do that's kind of interesting, and this is one of these like things that shows up on LeetCode. You could call this like matches or something, and do your inner product. And this is what the second example is on CPP reference, but I don't want to look at it quite yet here. Begin, and our accumulator can just be 0. But basically what I want to do here is Well, what do I want to sum up here? I do want to sum up the number of matches that I have here. Okay, so meaning if 0 matches with 5, these first elements, that would be a match. Then I compare these elements. 2 and 2 would be a match. 3 and 3 would be a match. There should be 2 matches here. So I want to add the number of matches. And the binary operation that I'm doing here is going to be equal to. Okay, which is, again, one of those functional things here. Or, again, you could specify your own operation here. So let's go ahead and print this out. Let's call this matches and print them out here. And we have 2 matches, okay, which is perfect here. That's exactly what we want. Let's make sure that's, that's exactly what we have here, the equal to, okay? Now I want to do one other thing here. They don't have an example here, so let's write our own, binary function here. And let's just change the problem a little bit here, okay? So I'm going to just paste in that function signature. Okay, this is going to be my binary function here. The return value, it could be things that are like true or false or whatever. Let's say greater. Okay, so I want to search through this collection and find the times that 0 is greater than 5 or 1 is greater than 4, 2, and count those up here. Okay, so I'll return. Let's think about the return type. Let's just call this greater. And basically, what I'm going to return here, and again, I'm going to be, these can be just integers here. Again, you can make this generic. You can pass in the template function. And basically, let's see. What do we have to do here? I mean, this is just returning a value that's going to be then applied in this next part. I mean, again, the reason I guess it makes sense to have this plus next to the accumulator is because the accumulator is accumulating the result of the operation that you're doing on the pairs, if that makes sense. Okay, so you can think about this operation 0 and then plus the first product. And then that's your new accumulator, and then you keep adding that sum of products. So it's actually a pretty well designed function, for something that takes in a lot of parameters. So again, just thinking about this, what is this returning? Again, this is just going to return us a true or false value. So return A greater than B here. And I guess we could be efficient. I mean, these are just integers here. Should we pass by reference? No, we should be good. There's usually a core guideline about just passing in a value here. So again, passing in by value primitive types. So anyways, let's go ahead and do this again, but I just want to show you passing in a custom function. Let's see, greater values, we'll just call this. And there is greater in C++. I think it is in the functional. Let's see. Is there? Yeah, there is greater already implemented here. But again, that's just what I could think of on the fly. So instead of doing equal to, we're just going to pass in greater. And let's see the greater values. And again, let's make sure we spell things right. It's just in case somebody searches here. Greater value. Greater values, because we could have more than one. Hold on, let's do this again properly. There we go. Let's go ahead and give that a compile and a run. And it looks like there is just 1, which we can confirm, right? If I look through, is 0 greater than 5? No. 1 then 4? No. 2 then 2? No. 3 then 3? No. 4 then 1? No. Okay, so that's the idea here. And then again, you could just pass in the function. Again, you could use all the other stuff that we've learned in the series. But let's be complete. This is going to be a fully complete lesson on inner product. Let's do the greater values lambda version. Lambda. Let's call this greater equal. Let's just do something just a little bit different here. And basically what I want to show you is instead of passing in greater, right, we want to pass in a binary function here. Auto A. Oh, we know these are integers here. Actually, let's see if I can just get away with auto B. And then as part of this, let's see, I will just return A greater than or equal to B. Okay, so there's no function there. Give that a run here. And we have 3 for this here. So there are 3 values that are greater than or equal to pass this sort of test here. Okay, so 0 is it greater than or equal to 5? No. 1 is greater than or equal to 4? No. 2 is it greater than or equal to 2? Yes, that's 1. 3 is that greater than or equal to 3? Yes. 4 is that greater than or equal to 1? Yes. Okay, so that's where the 3 values come from. Okay, but again, just showing how to pass in these different functions here so you get used to it. Again, the return type is deduced here for us. So that's all good and well here. So what's the point here, again, of this inner product stuff here? I mean, if I'm going to do this sum of product, right, I can easily write a function here. I mean, that's the argument here of saying, well, why don't I write this function here called, dot product, and I would take in, an array here or something, or a pointer to an array, or again, if we're being good C++ folks, right, a span, of one range and a span of another range here, and maybe the type here, right, we template it or whatever. Let's just assume these are integers, int A, int B, for each of these arrays. And then I got to think about, okay, do I want to do this C style? And then I got to pass in like the size. Or maybe I just do pass in an iterator. I mean, the point is, it's nice to just have this function built in so we don't have to think about this stuff. We could benchmark it. And then even thinking about the algorithm here, which I'll write out here. Let's actually just do it here. For int I is equal to 0, I less than a size, I plus plus. And then I need to basically do, let's see, I need my accumulator out here. So I need to initialize it. And then my accumulator is going to be equal to, let's see here, a at I. My operation, let's see, it's going to be multiplies of b of I. And I am summing these up here, plus equals here. Okay, so let's go ahead and just print that out. And I'll call this manual accumulator. Okay, and then just print out the accumulator. Did we get the same result here? Do I get 21 here? Let's see. Oh, if I don't make any mistakes, maybe I do. But it looks like, I mean, it still works, right? This was a simple enough operation here. But I kind of like having the one-liner here. I think I can handle probably, any type here, as long as I have the iterators here. So that's kind of nice. Versus maybe having to rewrite this code. It's not too bad. The raw loop here, maybe you could argue like, okay, I mean, this is kind of a wasted allocation here. Maybe we want that to go away in the scope of the main, whereas the function call takes care of that. Okay, maybe you're gonna also argue, there's no like pragma, open MP. I haven't used OpenMP in a while. I forget what the exact thing is, but you use like parallel for or whatever, an annotation. Or maybe you start arguing about like doing the SIMD intrinsics and stuff. That would be a good thing for us to look at here. But there are parallelizable versions of, that we're going to look at of inner product, right? Well, we already had a hint here, so you have to check out the next video here. But the point is, I mean, this is nice and easy to write. And if we're doing a lot of these, maybe we'll consider writing a super optimized version or something. And again, there's little ways that we can improve this that, are probably taken care of in the standard library, right? Using size t here, probably doing I, let's see, not equal to a.size -1, pre-increment, which might be faster. There's always debates about that. And oops, I made a mistake here. Okay, yeah, just that's what I mean here. Okay, so I mean, it probably gets these things right, these like little details here that, in a large code base are hard to find, might not know about them or whatever. So again, inner product seems reasonable. I wouldn't blame you if you just wrote a for loop, but it's nice to know that this exists here, and that if we, instead of having to write all these different loops here, we can start thinking about, again, this paradigm of map reduce and start doing things like, well, which of these values are greater, or which are the matches here, okay, if you have two equal data sets, okay? So just something that you can think about here. So anyways, folks, with that said, hopefully you enjoyed this lesson here. go ahead and just show you all the code in case you want to take a snapshot of it. That's what we have here in our greater function. So there it all is. Here were our results. Again, works as expected. And as always, you could go ahead and check out these lessons and any more here. I've got a nice new C++ course here that I'll occasionally add to as well if you want to check that out. But of course, you can find all the videos on C++, including this one for free, and track your progress here on my website. So anyways, folks, with that said, hope you enjoyed that lesson. I hope you're enjoying C++ and having fun. This was a fun one to make here, thinking about inner product. And again, it's a paradigm, right? This sort of map-reduce paradigm. So some of you are functional programmers are screaming that this is obvious. For those of you who have lived in C++ like me for a long time, you don't know about this stuff. So kind of nice to find. So anyways, folks, if you have nice little examples that you want to share, feel free to engage in any of the discussion forums on that. And thanks as always for your time and attention. I'll look forward to seeing you in the next episode.